chapter one of the book introduces the whole study of reinforcement learning and helps define in more general terms what it is with some examples before we get into the detailed mathematical notation of everything. So, the most general statement we can make is that it is some computational approach to goal-directed learning from interaction. And here the interaction we're talking about is there is some specified environment that we are interacting with. And then to get a little more specific, it is learning behavior or learning what to do when the environment is in a given situation. So when we talk about behavior, this is a mapping from situations to actions. And the goal of the behavior is to maximize some numerical reward signal, where that reward signal is what helps define the goal of the goal-directed behavior. And when we get further into the book, like in chapter 3, when we start formalizing the discussion, it will be really a study of Markov decision processes, and the reinforcement learning techniques will be, any number of techniques that help optimize behavior in these MDPs. And by optimal behavior, we mean something that maximizes the long-term reward within these processes. Oh, here. So, this is like, in very general terms, what the study of reinforcement learning is. And then another thing mentioned in the chapter is what it is not, because most people are probably more familiar with these other types of machine learning. So, supervised learning is something where we have a set of labeled examples, and the labels are from some, expert that already exists that helps define what the truth is for this study. And then the goal of supervised learning is to learn a function which generalizes this truth to other examples that haven't been seen. And those other examples should be somehow, characteristic of the examples we've already seen. If you formalize it with probability theory, they should be examples that are drawn from the same distribution as the trained examples. And then the techniques that we select would be ones where whatever function we're learning is something which is good at generalizing. And that how good it generalizes might also depend on the type of distribution that we're looking at. But neural networks generally are pretty successful at this type of generalization across a lot of different problems. Then there is also unsupervised learning, in which we have a large collection of unlabeled data. And in unsupervised learning, the goal is to find, some set of structure within the unlabeled data. But the goal might be a little vague, like we don't know ahead of time what it is. It could be, for example, putting the data into labels or categories where there is some sort of commonality between certain groups of examples and not among other examples. So finding, clusters of examples that are similar to each other. Or, in the case of like reinforcement learning, there is a role for unsupervised learning to play. So we could study an environment and try to learn just what are the rules of interaction, like behavior in the environment, like how do the probabilities look? And this would be an example of, understanding how the rules of the environment are structured. Now, even though both of these techniques actually come into play with reinforcement learning, neither of them are related to maximizing this reward signal, which is what I mentioned earlier. So the goal-directed part of it is not included in these. But a lot of the techniques later in the book will still include, elements of both supervised and unsupervised learning. So when we talk about like in a reinforcement learning agent, this is something that is going to be able to interact with the environment for the purpose of receiving feedback from that behavior. And then over time, the goal would be to refine that behavior to achieve the goal in the environment. And the exploration part of this, is where it takes actions and tries to, explore parts of the environment that it hasn't seen before. Whereas refining its existing behavior would be more an example of exploitation, where you already know something which is good or somewhat good, and you're trying to make an even better version of that. However, you can't do either of these exhaustively because you'll get stuck. So a lot of the methods that will come later in the book will involve techniques of balancing these two approaches, of both exploring the environment and exploiting what we already know is successful behavior. And this exploitation trade-off is also something which is not really present in supervised or unsupervised learning. So, to make this a little more concrete, we can think of a few examples. I've taken, these are in the chapter, but I've kind of expanded them a little bit. I'm just going to look at two of them. So one is like a chess player, or, some kind of expert chess player. And in this case, the environment would be the current state of the board, as well as the opponent, in the sense that after we make a move, the opponent will respond. So, our opponent plays a role in manipulating the environment as well. But from the perspective of the single player, both, the board itself and the behavior of the opponent are both, components of the environment. And then in this case, the goal is to maximize wins and minimize losses, just like is typical of games in general. And the behavior is pretty obvious here. It's just the actual moves that we make on the board. So then, optimal behavior would be something which maximizes wins and minimizes losses. And we could define this for a variety of opponents. So, you could train against weak to strong opponents, and then your behavior should be good in the sense of the goal, regardless of who your opponent is. But it's also possible that the agent would know something about their opponent, like, oh, I'm playing a very weak opponent. And then there could be certain behavior which is better against those opponents than against strong opponents. Like there are traps you can set that will fool a novice, but to an expert player, it would actually be a bad move to make because it wouldn't put you in a winning position. So this is a case where, depending on, you can frame the problem in different ways where, in the case of if the opponent is known or we know absolutely nothing about our opponent, there's also optimal behavior in that case. Now, the next example is something, completely different, of this cleaning robot. This will also come up, I think, in chapter 3 as a more drawn out example. But, imagine we have some kind of mobile robot like a Roomba, like vacuum cleaner, and it collects trash from the floor, but it also has to manage its battery so that it doesn't become inoperable. And there's some charging station that it can return to. So in this case, the environment would be the charge level of the battery and, some proxy of how difficult it is to return to the charging station. This could be something it knows explicitly, like the distance it has to travel to get back, or it could be an estimate based on how long it's been gone and, the shape of the house it's in. And then the goal would be to collect the most trash over a long period of time. And that, long period could even be for an infinite amount of time. So, if we set the time to be very short, then the charging might not even be a concern. Like it could, you don't want to go and run its battery all the way down. But if we say that this problem is going on for an indefinite period, then obviously, if the robot ever goes dead, then it has no ability to collect anything for all of the future time periods. So even just setting this up as a problem that goes on forever, that would already be a situation where the robot going dead would be like a completely unacceptable outcome for this, because that would always be worse than like any other outcome that you could have. And then the behavior in this case is not very complicated. It's just the decision of whether to continue on its operation of collecting trash or to return to the charging station. And in this case, we would assume that the mechanism of how the robot moves or identifies trash and collects it, all of that is handled um, by some other process. And here, the goal of the reinforcement learning itself is just to learn this very high level decision of whether it should keep going or stop to collect trash, or stop to return to the charging station. So are there any questions about these couple of examples or anything I've said so far?
Not currently, since the cleaning robot example and the chess example makes sense so far.
Mhm. Okay, well, I can keep going. If anything comes up, just feel free to interrupt and let me know. So among all these examples, and if you read the chapter, there's a few other examples mentioned, but they all have a lot of certain elements in common, which is that even though there's a lot of uncertainty about the environment, the behavior is still able to try to seek whatever this goal is. And there's uncertainty about what happens immediately, and there's also uncertainty about what happens in the future, because the goal involves all of the future states and all the future rewards that the agent receives, and it can't possibly know that exactly. But the optimal behavior would be trying to achieve would be something that behaves optimally even among all those uncertain possible future outcomes. And of course, in order to figure this out, the agent would have to spend a long time interacting with the environment or have some kind of model of the environment that would be close enough where it could collect enough information um, in order to figure out what is the distribution of possible outcomes. And right now it seems like a very difficult task because we don't have any of these techniques, but the focus of most of the techniques in the book is going to be to calculate something called the value function. And that is going to be the basis for a lot of the solution techniques. But for all of the elements I've mentioned already, like I mentioned, the behavior of an agent. And in the book, eventually that will be referred to by a more technical term when we talk about the policy function. And the policy function is just something that maps the environment state to an action, either to a defined action or to a distribution among actions if we have a stochastic policy. And then the goal, I already mentioned the reward signal, but like all these problems will have some reward signal, which is some numerical feedback, which is received after every action is taken. And that reward signal, however complicated it is, in its totality is what defines whatever the environment goal is. And in some cases, it's really straightforward, like in a simple, like a two-player game, right? The reward signal can just be like 1 if you win and -1 if you lose, or 0 if you lose. But in other problems, it can be something more complicated, like in the trash robot, it could be like the amount of trash collected per unit time could be the reward signal. Now, the value function is something which doesn't come directly from the environment, and that would be an estimation of how much future reward can we expect from a given state, and also with a given policy. So the goal of the agent and a lot of the techniques in the book will be to have a certain policy that they're following, and at the same time be estimating the value of all of the states or situations that they find themselves in the environment. And this value function approach is something which is a number which is different for every state in the environment, or some estimation across states if we're trying to generalize. But in simple problems, we can have a specified value for every state. And there are other approaches you could imagine, like we have a bunch of agents with different behavior, and then we let them interact. We see which agents are the most successful for a given period of time, or for an entire episode or a set of games. And then we select agents that are successful and combine them somehow, like in an evolutionary approach. There could be parameters or subroutines of different behavior functions that we combine in some way, like in like a genetic algorithm approach. The downside of those approaches is they're very inefficient because they don't exploit any information about what happened along the way, like the detailed behavior that occurred at every state. Whereas the value function is something where we're trying to learn the impact of the actions we took at specific states within the environment. And we'll see that it ends up being, a much more successful and efficient approach than trying to just, more randomly search the space of behavior, which could be a very large space of things to look for. See, Tom has a question. What about situations when the reward isn't available for after every action? Well, so if you have like some continuous time task, typically what you would do is you would have some time interval that you set, like 1 millisecond, and you would turn it into a task which has discrete steps. And, even though maybe in the real world, this is a continuous process, as far as the control system we're using or the sensors we're using, there probably is some sampling interval in which we're collecting data and some sampling interval also at which we can take actions. Like we can't just freely do things, in continuous time. And then those would become the steps. And then it's not that the reward isn't available, but like we could try to provide a reward on that interval. And like in the case of the chess game, like you could say, it's not that the reward isn't available after every move, it's that the reward is just zero until we see if the game was won or lost. And then the reward we would get at the end. So there is a difference, I'd say, between the reward being unavailable and the reward being zero. A lot of tasks will have a reward of zero for a long period of time. And that would be referred to as like a sparse reward versus a task where we can sort of see useful information like every moment. I mean, if you go, right, even in the example of the chess game, we don't get valuable reward feedback until the game is over. And that can also be true of a lot of other control tasks, like even like a maze solving task or a pole balancing task. You don't really get any feedback until, the pole falls or we exit the maze. So that is very common among these problems. Does that answer your question or
Well, I
more
think
to it?
the elevator control problem is more complex because you have multiple ones, multiple elevators, and how one behaves changes how the other behaves. So it's hard to have something until, I guess, every trip is completed. Um,
Yeah, but if you're sampling this, like you have trips being completed all the time, and just when that happens, you get a reward signal, and there's some time interval at which, like in this case, maybe the environment state would just include all of the elevators
yeah.
and where they are and what if they've made a successful trip or not. So yeah, it doesn't really fundamentally change any of the problem setup.
Okay.
But you'll see later, like because we're going to develop these very generic approaches, a lot of the work that we have to do is actually how do we take the problem we have in mind and define all these things, like define the states, define the reward signal. But
Okay.
as soon as we do that, we'll be able to solve the problem. I'm not
Yeah.
saying it'll always be obvious how to make those definitions. And there are certainly tasks for which this wouldn't be appropriate. Like if we don't have a simple goal, like something that we can write down as a numerical goal, then we can't use any of these techniques. And there are certainly tasks where there's not like a goal in that sense, but a lot of things do have, we could write down a goal for most of these tasks, especially if it is a control system type of task. That's usually something for which we can write down a goal.
Okay. Thanks.
Okay, so I think that is it for as far as these slides are concerned. We can now look a little bit more at this this extended tic-tac-toe example, which is the basis for the exercises, which hopefully some people looked at the exercises. Because I'll pause a little to ask, if anyone has an answer they'd like to provide, but I will be going over at least my answers to these exercises. So in the tic-tac-toe example, I hope most everyone is familiar with how tic-tac-toe works. There's just a 3x3 grid. The X player goes first, and then each player can place an X or an O in one square. They alternate on every turn, and then if you get 3 in a row, you win the game. And here they're saying, we could consider draw it, like tic-tac-toe has draws as well, where neither player wins. So you could either treat wins, losses, and draws as all separate situations. Here they're imagining that draws and losses are equally bad. And then the goal would be to construct a player that maximizes the chance of winning, where if the reward of winning is 1 and the reward of a draw or a loss is 0, then in that case, the value of a state would just be the probability of winning in that case. And the goal would be to have an agent with behavior that maximize that probability at every possible state. And here we're saying that we have an opponent. Now we don't, like, it's possible the opponent is a perfect opponent, but let's imagine we have an imperfect opponent. How would you go about finding the optimal strategy that exploits your opponent in the most effective way possible? And for tic-tac-toe, we know that with optimal play, every game is a draw for both players. You can use, one classical solution technique is minimax search. And this is a classic technique for 2-player games. And it would find optimal behavior for each player, assuming that they are also playing an optimal opponent. However, the point here is that the minimax solution will not exploit things that an imperfect opponent will do, right? Because we don't actually have our opponent as part of the solution technique. This is just optimizing both players simultaneously. And we're also saying here, let's say we are told that we have a specific opponent, but we don't necessarily know how they behave. Like, we can't write it down on a sheet of paper, but we can observe how they behave. And in that case, the only way that we could get information about them is by playing against them and somehow, trying to keep track of the moves they make and learning some kind of model for how they behave. Now this discussion goes on to sort of explain what are the flaws with taking an evolutionary approach. This would be like where we set up several different policies to play our opponent. We play maybe 100 games. We see which of those agents were the best, and then select them, combine them, or modify them in some way, perturb them, and then keep going. And then over time, we would evolve some kind of, a better policy. So that's one approach that we could take. However, the claim is that this value function approach is much better. And the description, oh yeah, hello, you have a question? Shahar? Oh, no, okay, never mind. So in the value function approach, we would set up a table of numbers for each possible state. And that number would be an estimation of the probability of winning, right? Because the win is 1, loss is 0. We basically have the percentage of time that we win, or the fraction of times we win, would be what the value function represents. And then, if certain states are higher value than other states, then we can take moves that bring us into higher value states. And, that would be the general approach. There aren't enough details here to know exactly how to do this. But then, of course, along the way, as we try to learn this policy, we have to make sure that when we're making moves, exploring the game board, we don't always see the same states over and over again, right? Like, our policy itself has to have some degree of random moves in it, as to ensure that we end up seeing situations where, right, in order to fully learn our opponent's behavior, we have to make sure that we don't just repeat the same states over and over again. So this is where the exploratory moves come in. And then, you know, we can set some specific value, let's say, where we make exploratory moves on some interval of time, like maybe like 10% of the time. But with the value function approach, we would initialize the values. If we initialize them at 0.5, that would be, like in this game, a neutral value, because it would assume that we win half of the time. And then as we learn from the opponent, right, we can make moves, and eventually we get to a situation where the game ends, either with, you know, a win or a loss or a draw. And then there's this update rule we can do, which is we have some existing value estimate, like it starts out at 0.5, and then we can update it with the value of future states that we see. What's missing here actually is the reward that we get for a game state ending. But you can imagine, like, along the way of making moves, right, we don't get any reward signal. It's just 0, right, until the game actually ends. So for the value function to be correct, it should actually be a fixed point of this update rule, where the value of one state, if we look at all the possible states that we could end up in, and take those into account and add them up, then it should end up being the same value, right? Because the value shouldn't change over time, because, like, we've already accounted for all of the future outcomes that we have. So this type of update rule is called temporal difference learning, and it's one of the techniques we'll see later. There are also other update rules that we'll see that involve collecting data all the way to the outcome of a game. But, you know, the actual justification for this will come later in the book. And another advantage of this type of update rule is that we can begin refining the value function in the middle of the game. So, you know, or Tom asked, like, well, what if we don't have reward available? Like in this example, we don't have any reward signal until the end of the game. But as we learn a value function over time and the values become more accurate, we can actually exploit the relationship between states to get some intermediate feedback with this this temporal difference update rule. If we do other approaches where we don't use, like, the relationship between the states, that's a different type of update rule, and then we wouldn't have any information until the actual outcome of the game. But with this update rule, we can get information, and this, you know, is using the relationship between the states, and it depends on what happens within the game, like within individual games. And if we take the evolutionary approach, where we just have some policy, you know, or we have like 100 different, you know, candidate agents, and we just try to pick the ones that did the best, then all we know is how well they did overall over a large number of games. Like, we know that this agent is more successful than this other agent, and then we could try to evolve that agent forward. But we have no idea in that case why the agent is successful. Like, are there a particular set of states for which it's very successful? And since we have access to the state information, the claim here is that we should make use of it. And value function is one way of making use of that. And then, yeah, like, the other point here is that, yeah, we don't have any, like, we can also apply these techniques without any knowledge of our opponent. We could just work from a situation where all we can do is interact with the opponent. Right. So we have to, if you compare it to something like supervised learning, part of our learning process has to sort of generate the examples or the data set that we use. And if we don't explore the environment properly, then we would have a very bad data set where we could only learn a limited amount. So that's why these techniques are, you know, they're there's a lot more elements beyond what we would just see in something like supervised learning, because we have to also balance, how the behavior works to collect the appropriate data to learn what we need. So now let me see if I explained enough of this example so that these exercises make sense. But we'll start with, well, the first exercise is about self-play. So we had said originally that we were playing a fixed opponent and we wanted to exploit them. And now, or, that fixed opponent could be a random opponent, let's say. So now the question is, suppose instead of playing against a random opponent, we played games against itself. So we had, some policy function which had could specify behavior for both X and O positions. And then both sides tried to apply these learning, update rules with the value function. And, what do you think would happen in this case? And would it learn a different policy for selecting moves than when we play the random opponent? And, in this case, we would, I guess, both behavior policies originally would be random. They would start playing. So both are, and in the beginning, are facing random opponents, but then both policies learn along the way. So then the question is, we have the one approach where we just play a random opponent, we learn certain moves, and compared to the approach where both sides are able to learn or modify their policies. So first of all, I don't know if anyone actually did read these exercises and have time to think about them, but also if anyone has an answer to this or was confused about it and wants to either say their answer or get feedback, can let me know now.
Well, I would assume that the policy would probably be different, compared to a random agent. And so the only question that I had was that, would those, two policies basically optimize, or would they, just collapse to be basically, continuing to be a random policy?
Or you mean like, would they cycle like back and forth?
Yeah.
In some way? Yeah, that is something to consider. Did anyone else have an answer? So I believe with, the minimax approach mentioned is sort of, it's not really self-play in the sense that there's actual samples being taken, but it is something that, achieves this optimal solution between two players. And I believe that having, starting out with random opponents and having this value update on every move between them, this should end up achieving the same type of solution as the minimax solution, where both sides end up learning optimal behavior against an optimal opponent. So, it should converge to the same thing as the minimax solution. You'd have to make sure that as they were being trained, both policies were still taking exploratory moves, and then the fraction of the time those exploratory moves are made would have to decline over time to really make sure you converge to that. But yeah, it would certainly be a different policy then, right? Because every time you were collecting samples, right, the opponent, after some number of updates, is no longer going to have random behavior. So then the behavior the X player would exhibit would then be different. The optimal behavior to exploit that new player would be different than if they were playing a random opponent. Without seeing, I can show, I actually have a notebook that has some examples of solutions with the tic-tac-toe agent. So, until you actually see how the solution works, you might not believe this or it might not be obvious, but I think, yeah, this shouldn't it doesn't really end up cycling or having pathological behavior, but it does converge to optimal play. Okay, so the next question is about symmetries in the game. So many tic-tac-toe positions appear different, but are really the same because of symmetries. How might we amend the learning process to take advantage of this? In what ways would this change improve the learning process? So that's, I guess, part one of the question. Now, by symmetries, we mean, actually, I can show this. I'll show this notebook to explain some of the symmetries. So the tic-tac-toe board has these D4 symmetries. And that means that, if we represent the board as, a vector of length 9, so we count states like across the rows, as an example. So like 1, 2, 3, 4, 5, 6. So then we could define a board by saying, well, there's an X in state 1, an O, or an X in position 1, and O in position 2, right? 1 to 9. And what these symmetries is if we reposition all the squares, so that, like we move 1 to 3, 2 to 2, 3 to 1, right? That's what these vectors define how we move the squares around. Then these boards should all be considered equivalent, right? So like you also have the rotations, right, with 90, 180, 270. So if we take this board and rotate it 90 degrees, even though it looks different, like the X's and O's are in different positions, it actually is the same board, right? These symmetries are all transformations which don't fundamentally change the board, but there's many more symmetries than just the rotations. There's also flips along the diagonals and the vertical axes, and the trivial identity symmetry is true of any for everything, but that's just where we don't move anything. So does this make sense to people how the boards are all equivalent if they obey these symmetries? So then going back to the question, it's how I amend the learning process to take advantage of this. How would this change the learning process? So, right, so like let's say we're representing the game board by this like vector where we count across and we specify where the X's and O's are, then how might we use the symmetries to change the learning process? Okay, well, if no one has an answer here, can just read my answer here. So we said, we're going to have a value function table where we try to estimate a value for every state. So we could modify this so that for all of the symmetrically equivalent states, we treat them all with the same value, right? So this would reduce the number of states in our table, right? Because we wouldn't need to have a separate value for all of the states. Like if I take this board and I rotate it and I apply all of those symmetry transformations to it, I can take all of those as being equivalent to the same state. So one advantage of this is that our value function is simpler. We don't need as many numbers to represent it. So it would be more efficient. That, so the main advantage is a more efficient use of data. It doesn't matter that much with this problem because the number of states is still pretty small, but you could imagine in more complicated problems where, this would help like collapse the state space by a larger percentage. But then the next part of the question is, suppose the opponent did not take advantage of symmetries. In that case, should we? Should symmetrically equivalent positions have the same value? So in this case, like we might like have an opponent where even if we rotated this game board 90 degrees, they would actually play differently on that board than on this board. Even though we know that, mathematically they should be equivalent boards. So, the question is, in that case, if our opponent doesn't respect the symmetries, what should we do?
Well, if it doesn't respect the symmetries, then wouldn't there be a problem where it would not, where an agent that assumes symmetries might basically miss the case of basically someone having two in a row already in one corner because of the lack of symmetry. So like if someone plays at the bottom left corner and then the top middle the other agent might basically play to the right center or something like that because of the assumption of rotations.
Yeah. So what I mean, the point is that we're told that our opponent behavior may differ in symmetrically equivalent positions, right? So whether or not, like, whatever the details are doesn't matter, but if we exploit symmetries as the learning agent, then all of these different transformations of a given, like, this is actually a board where there's already been a winner, but we can imagine, like, if this X, if this board was in an earlier state, then we're trying to exploit our opponent. So let's say like they happen to make like a bad move, a worse move in one of these symmetrical transformations than in another. But because our value function is considering all of those to be equivalent, we would be unable to exploit a situation where our opponent, like, we would be wanting to get the board into a state where they behave less optimally. But if we are using symmetries, then our value function can't direct us to those states because to us, like, we have no ability to model them. And all of our opponent behavior that would be different between the different equivalent states would all be averaged together in the symmetrically equivalent states. But if we store them all as separate states, then we have the option of learning that, oh, actually our opponent, they are more exploitable in this position than this other position, even though they should be the same. But, now in the tic-tac-toe, it might seem strange that someone would do that because the board is very simple. But, there are other problems where there are very complicated symmetries that a person might not see as obvious, and then they actually would behave differently in symmetrically equivalent positions. So yeah, but unless we would have to know that ahead of time in order to make the decision not to use the symmetries. In that case, let's see. I mean, more, I guess I wrote this out as our opponent reacts differently. If our opponent reacts differently to moves in one position or another, then it's important we estimate separate values for each state, right? So we would need to uncollapse those value estimates because it actually does make a difference for our opponent. Yeah, if our opponent is optimal, if we have the minimax solution, then obviously all of those opponents would not behave differently in symmetrically equivalent positions, because to the optimal player that doesn't matter. But here for this exercise, we're being told that we don't have a random opponent, but maybe one that could behave differently.
Well, if it's learning in the same time, then it has to explore also.
Oh, yeah. Well, that was the self-play thing. Here we're back to the case where we have a fixed opponent.
No, I'm just pointing out that the definition of exploring is playing suboptimal. Right. So the opponent may play suboptimal. You were just saying.
Oh, you mean if they're learning? Yeah. Well, that's if they're also trying to go through the learning process.
Right. I'm just saying there are cases where you could see suboptimal play from an opponent.
Oh, I mean, in this case, we're definitely considering that. I mean, that there is no point here where we've said we have a perfect opponent, but the question is whether the opponent is perfect or imperfect. Right? You can have an imperfect opponent that still doesn't behave differently for positions that are symmetrical, right? But you could also have an imperfect opponent that does behave differently in symmetrical, like positions that should be symmetrical. So it's sort of a, it's a different, like it's an orthogonal question to the fact of whether they're optimal or not. But yeah, any, like imperfect play could be ignorant of the symmetries, or it could, it could always behave the same with those symmetries. But here the question is more on like our approach to the problem, should it respect the symmetries or not? And the point is that that does depend on whether if our opponent is respecting them or not. So any other questions about this exercise? So the third question is about greedy play. Suppose the player was greedy. That is, they always played the move that brought it to the position that it rated the best. Might it be better or worse? Might it learn to play better or worse than a non-greedy player? What problems might occur? So when we started out, right, like if we start out with a value function, which is all 0.5, let's say, then initially, even a greedy move would be still be random. But over time, as we learn, we haven't finished the learning process, but in the middle of the learning process, we have an idea of what move appears to be the best right now. So the greedy player would only take the greedy move. And yeah, the question is what could be potential problems with that approach, and would it, how would it do compared to the player which makes exploratory moves?
Wouldn't the greedy player basically end up in a situation where they can't anticipate, the move of, basically having, two, bottom, the bottom center and then the center left case in order to where, that player is trying to basically make the situation where, basically having a situation where either or would end up being a loss.
Wait, I'm sorry,
Oh,
I didn't quite follow what you were saying.
oh, well, I was just thinking that, a greedy player would, miss out on certain moves, essentially.
Yeah, so a greedy player might never test out certain moves. Yeah, that is true. They would only make the moves that it thinks are best at a given time. I mean, they would still get feedback from those moves. But
To put it a little more briefly, if you are always greedy, then you are never exploring, right? You only explore if all is equal.
yeah, which would be the case at the beginning. But yeah, very quickly you would start only making the same types of moves. Yeah, but then the question is what would you end up learning and what? Oh wait, no, we have. I mean, so right, this is a question of what occurs during learning. So we should assume that during the learning process, right, our value function is not actually correct yet. Like it's just we are trying to learn. So by like we haven't learned everything. So when we start making greedy moves, we are making greedy moves based on what we currently know, but that may not be the whole picture.
And if I make a bad move to begin with, I might try to do it repeatedly and
Well,
probably.
also remember, like let's say we initialize the value function at like 0.5, so that's neutral. If we make a bad move and that bad move results in a loss, then no, you wouldn't repeat that because a loss is worse than 0.5, right? If you end up winning and losing equally often, it would be the same. If it ends up winning more often, it would appear better. So yeah, if we make it's not as though if we make greedy moves, we still get feedback from them.
Okay.
It's just that. So here, I'll just to maybe clarify this. As we basically, if you happen to make moves that are marginally better than the random behavior, then those will appear to be the best. And the greedy policy would end up taking them. Like, and let's say they do actually improve the win rate to more frequently than half of the time. But that doesn't mean that you've reached anything optimal. It just means that it's something better than like now you could end up still further improving it, but there's a risk of getting stuck in like a local optimum where you found something that is better than your initial random policy, but you never end up, visiting other states that could have potentially even better outcomes. And, so you'll never actually end up getting accurate estimates for the entire space of states. So the problem is you can never be sure that you actually have something which is optimal. It may just be better than what you had before.
Well, I think with tic-tac-toe, this doesn't really apply because there's only one state win or loss. If you had something like cribbage where you could win better or worse, but
no, there's only win or loss. But remember, the value function would be the percentage of time we win or lose. So we could end up with a policy that wins 60% of the time instead of 50%. And then, but there actually is a policy that wins, 80% of the time that we never find because, we get stuck in those greedy moves that are like, they are better than what we started with. So yeah, this problem does apply to games that just have a binary outcome. But yeah, it would also apply to games with a more, complicated scoring outcomes. But yeah, like the value function doesn't represent the outcome of any one game, but it is a representation of what we would expect to happen on average, as we repeat games.
Yeah, I guess I'm getting thrown because tic-tac-toe is completely deterministic and you know what's going to happen.
No, well, we
no...
don't, right? That's only true if we know our opponent's behavior exactly.
Or we're playing optimally, but yeah.
Even if we're playing optimally, if we have a random opponent, we don't know what's going to happen. I mean, we know that we'll probably win, but right, we only know a distribution of what will happen because our opponent, can move randomly. But yes, if we have an optimal opponent, it would be deterministic because, and actually even then it's not, I mean, it may be helpful to actually show this notebook. So, here, let's see, after training here, I can set this. So after both, if you train it back and forth, so both agents achieve, something like optimal play here, this should be close to optimal. If we reset the board, right, so it's saying like for the X player, the ideal move is to go in one of the corners. Now, it is true that like whatever our optimal policy is, it wouldn't make sense if one corner was better than another because of the symmetries, right? So it depends. So yeah, in terms of symmetrically equivalent moves, there's only one move here, which is the corner move. And then, O would respond here. These are also symmetrically equivalent moves. But here, like the O player, like can draw the game from this situation. And all four of these moves are all result in a draw. But these aren't symmetrically equivalent moves, right? Like this move is different from this move. And they're both equal. So even our optimal opponent, could randomly choose between these two. So, we do know what will happen in the sense of a distribution of what will happen. But, we don't, it's not deterministic in the sense there's only one outcome because the drawn games will end up looking different if our opponent goes, in these side centers positions or in the corner positions. Right. So I think like you have to be like it is deterministic in the sense of having a draw outcome is determined, but exactly what the board looks like will not be predetermined because there are these equivalently good moves.
No, and you're right, because our opponent could screw this up at this point and lose, even though it's obvious that he shouldn't. It's possible.
Yeah. So like if O goes here, now we have a guaranteed win. And now, of course, we've also broken the symmetry of the board here, right? Because now this corner is not the same as this corner. So yeah, now going here is a guaranteed win. And of course, the way this is coded, O is now completely indifferent, right, to the move it makes because O could block a win here, but X would win. So that's why the way this solution technique works. I mean, the way I've designed it here is that the O player doesn't care if it actually blocks one of these, right? Because it doesn't matter. It's guaranteed to lose anyway. But what I showed at the beginning was, oh yeah, so actually this is the same. We can come back to this in a second, but yeah, so regarding the greedy player, the problem is that, right, like you can get stuck in something which is just marginally better than what you had before, but you have no guarantee of actually achieving the best possible behavior, right? Because we're never going to actually get, like, we're not even guaranteed to visit all the states, right? Like we could just find a certain route to victory, which takes us into certain states. There could be some other state we never see because we never got there, and it could have been better, but we would never even know that it was a better state because we never see it. So that's the problem with greedy only play. Does that make sense to everyone? Any other questions about this? Well, so the next exercise, well, this is really the last real exercise. The last one is just more of a brainstorming thing. But, oh yeah, so as part of this learning process, we had said that even though we make exploratory moves, in terms of updating our values and like improving our behavior, we only do that when we make the optimal move. So right here's an example of, on this step, even though we believe that this move is optimal, we make this move instead, just to collect data. And there is no feedback that occurs from this back to here. Like if we use this temporal difference learning update. So we only actually update our value function when we make greedy moves in this example. And the question is, what if we did this update after all moves, including the exploratory ones, so that we, and we reduce the step size parameter so that we converge. What conceptually are the two sets of probabilities computed when we do and don't learn from exploratory moves? And then assuming we continue to make exploratory moves, which set might be better to learn, which would result in more wins? So it's a multi-part question, but the first part is just, what did the two probabilities represent? So we already said that for the case where we only learn from greedy moves, the value function should be learning when we behave, when we have optimal behavior, what is the probability of winning from a given state? So that, I mean, we already said that that's what the value function should represent. So now, if we also learn when we make, like, let's say, we make exploratory moves, 5% of the time, then what does the value function represent in the case where we also learn from those moves? So I'll wait. If anyone has an answer or a thought on how to answer that, let me know. Okay, well, the short answer is that if we have a constraint, like we make random moves 5% of the time, we can still find optimal behavior for that case. It wouldn't necessarily be the same behavior, but we can still say, if we do the best we possibly can and we make random moves 5% of the time, what is the percent of time that we win? So it still represents the probability of winning. It's just the probability of winning, assuming that we are forced to make random moves a certain percentage of the time. Does that make sense? And then what might be better to do, right, in this situation? So let's say that when we're done, like once the agent has learned, it is then free to make greedy moves once it's learned, right? In that case, it would be better to learn the value function for the greedy policy, because we want to know if we're allowed to make greedy play all the time, what is the best we can do? But, you could be told for some circumstance, maybe not tic-tac-toe, but another problem where that when you are actually interacting in a real environment, you will have random behavior some percent of the time. If you know ahead of time that that is a constraint, then it might be better to actually learn the value function for the constrained case, right? Because like, if we're going to make random moves 5% of the time, we don't want to know the optimal greedy policy. We want to know the optimal epsilon greedy policy, which is, it's a term that is defined later in the book, but the epsilon greedy policy is a policy which makes random moves epsilon percent of the time. So if epsilon is 0.05, be 5% of the time. And if epsilon is 0, then that can be the greedy policy. So the epsilon greedy policy includes the greedy policy. If we set epsilon to 0, we can also make epsilon any number from 0 to 1. And depending on what it is, there could be a different optimal policy for every value of epsilon. So oftentimes we do want to have epsilon go down to 0, like towards the end of the learning process, because we really only care about the greedy policy. But we are free to also learn, any number of epsilon greedy policies. And you could also do that for tic-tac-toe. I didn't actually do it here, but I would be actually, maybe I should add that, because I would be curious to know. I'll make a note here about what is the epsilon greedy policy. Yeah. Yeah, I think that would actually be interesting to see. Like, if we know, like, if we have to move randomly, like half of the time, it could end up producing different moves. And basically, there would be certain situations where moves that would normally all be equally good, because we know what our future behavior will be, some of them will not be as good, because they could put us in a more risky situation where, we don't want to take the risk of, like, the higher the value epsilon is, the safer our behavior has to be, because we can no longer guarantee what we do in the future. So this is also, as part of this example, I did set this up so that, like, what this is showing is the optimal behavior against a random opponent. And if I switch this, it will show optimal behavior against an opponent which has been updated. Like, it's also managed to learn. It hasn't learned, an infinite number of times, but in this case, there's been 4 sort of back and forths of learning. And what I'm showing here in this diagram is, this is a comparison of the 2 policies. So this is a comparison. On the right is the policy that is optimal against a random opponent. And on the left is optimal against a better, if not a perfect, a near perfect opponent. And this is only showing states for which the policies are different. And the number above is the value estimate here. So we can see, like, certain situations here where if our opponent is good, right, like in this state in the lower left corner, we know that we will lose this game, right? Because O has 2 ways of winning. So therefore, we're indifferent to the move. But if our opponent is random, right, notice that here the optimal policy is to block one of these winning moves, right? Because there's always the possibility that our random opponent accidentally plays here instead of winning, right? That's why this value is 0, because this is saying we have an equal chance of winning and losing depending on what our opponent does. So we wouldn't want to move here, right? Because if we move here, then we actually force our opponent to make the winning move on the next move. And there's some other interesting situations here. Actually, I guess, so another example is if we set up the board like this. So, neither player has made, well, actually O has made an optimal, I believe O has made an optimal move. One of the optimal moves here. So in this position, if we play against a random opponent, we actually want to move in one of these corners. But against a better opponent, it's better to move into one of these squares, right? And that's because in this situation, we're fairly certain that the game will be a draw, right? So this is like a defensive move. But if we're playing a random opponent, it actually thinks that there's this like 94% chance to win the game. But actually, if I move here, like, because if I move here, think about it, like, we have a chance to win on the next move, right? And our opponent, if they play randomly, could play in any one of these squares. So it makes sense that in this situation, we would favor here, whereas against a better opponent, there's no point in trying to go for this win immediately, because we know they're going to block it for a fact. And then we open ourselves to a risk, like here they'll block this, And now, you know, like the best we can do is, I mean, this is still going to end up being a drawn game if we play here, but this is, you know, assuming that both players play perfectly. But you'll find that for the random opponent, we always favor moves that lead to winning positions faster in the game, because there's a greater chance, like the more times we have a winning move available on the next move, then it increases the chance that our random opponent will fail to block it, and then we'll be able to win. Whereas against a better opponent, you know, we're always going to play these defensive moves. And that's like also characteristic of the minimax solution, because when you do the minimax solution, you only make a move which is good, you know, according to the best possible response from your opponent. So obviously, like, this is a good move if our opponent forgets to block this, which a bad opponent might do that. But the minimax solution will never even consider like a move up here, because it has already taken into account the fact that our opponent is always going to respond correctly to this. And then, you know, we can see, if you look at this whole grid of possibilities, you can see other, you know, situations. I mean, a lot of them are just cases where there's a single move favored out of many, because in losing positions. So anytime you see a -1 here, these are losing boards. And if the board is losing, the move doesn't matter, right? Because we're going to lose. But against a random opponent, we should pick the best out of these. And the best move out of these is always the one that delays the win, because, right, there's always a chance that our opponent will actually make a bad move. And then we could exploit that the next time. Let's see. Yeah, so unfortunately, I don't actually have a diagram explaining, seeing what how the changing the value of epsilon affects the optimal policy, but maybe I'll add that next time. It would be actually cool to have this same board thing and have a slider, so you could set the state and then actually see how the policy changes as we change epsilon. There's this final question. Can you think of other ways to improve, or a better way to solve the tic-tac-toe problem posed? I guess if anyone has any thoughts on this, you can say it now. I do have an answer, but this is more just a chance to brainstorm or ask any other questions about how the technique works, or if there are flaws in it that we could improve. You know, there will be some later techniques that involve having a model of the environment and sort of being able to collect samples in sort of a simulation phase that isn't a true interaction with the environment. But in this problem, our model and the simulation are really no different, right? Because we can model our opponent's behavior, interact with the environment. So for this simple problem, those types of techniques don't really matter, but there's other environments where it could be expensive to collect samples from the environment, and then we might want to collect more data in a faster manner from what we've learned so far. And that, I think, chapter 8, yeah, has examples of that.
Just a thought. Maybe we can opt for a non-RL approach. Maybe like create a table and capture all the possible optimal moves. Maybe like in state. Maybe like a lookup table. I mean, it would be sort of exhaustive, but maybe
you mean like an exhaustive search?
Sort of, yeah.
Yeah, I mean, the minimax solution ends up being an exhaustive search as well.
And that is a non-RL approach.
Yeah.
Okay.
Yeah, and that would however, if you think about the case of trying to exploit a random opponent, right, like you can't use the minimax approach, but yeah, you could do an exhaustive search over all of the random moves that your opponent could make, right, and weight them equally. And you could do it that way as well. Yeah, I guess Minimax doesn't have to be an exhaustive search, because if you find a certain move, I think, right, like if on your way to finding moves, you end up encountering one which is worse than what you've already seen, you can just throw away that whole, that's like, this is like the pruning part of it. But, you know, so at the end, you don't actually need all of that information. But yeah, like tic-tac-toe is a small enough problem where you could probably go through that. Although, I guess in this notebook, there's, let's see, we have the actual tic-tac-toe. Let's see, how many states are there? So if you only consider valid states and you also do the symmetry trick, there are apparently only 138 active boards. And then 138 inactive boards, like actual, I'm not sure if that's exactly correct. You can see throughout this, like you can start out by just getting like all of the boards. Oh no, sorry. So it looks like there's, yeah, no, 627 active boards. I think what I was looking at was something different. But let's see, symmetric. Oh yeah, symmetric boards. Yeah, so symmetric boards is something where I take, I only have one copy of every symmetrically equivalent board. So in this case, there's only 765 of those. Now, in terms of the actions, when you start out, there's 9 possible moves. Every move, there's 1 fewer. So the actual number of actions in the states is not that big. However, the number of games is actually much larger than the number of states, right? Because the number of games includes like all of the, like the order of how the moves were made, like along the way. So you do end up multiplying the space a lot bigger. So yeah, exhaustive search, even though it's still feasible for tic-tac-toe, it is like actually needing to consider like having an individual value for all of the different paths that you could have taken to get to a state makes, you know, exponentially grows that space. And that's one of sort of the magic tricks of the value function approach, is that once you're in a state, you don't care at all how you got there, or even like what could happen in the future, because all of that is like what happened in the past is irrelevant for these problems. And then everything that happens in the future is captured within the value estimate. And then, you know, you're exploiting the fact, the sort of the Markov property of these problems, where the actual path to a given state is not relevant to what happens after that. Oh yeah, sorry, I was trying to see if I could see how many of the total boards there are, not just the symmetric ones. But basically, when you define this problem, you can start with a naive, like the naive answer of how many boards there are is, you can set this up as a ternary vector, right, where you have either x, o, or blank in every square, right? So you can represent a board by a 9-digit ternary number, and then the number of total boards is just how many of those numbers there are. But in reality, there are far fewer valid boards than that, right? Because that also includes boards where every position is x and things like that, like imbalanced positions. Yeah, but you know, we can estimate it if you take right, it should be like 3 to the 9, right? Should be the total unfiltered possibilities, which is right 19,683 states. And we start with that, and then, you know, we end up in the end with the symmetric boards that we care about, and there's only 765 of them. So this is, you know, there's a very large reduction in the total things we have to consider. Yeah, in terms of the actual number of games, like if you're doing an exhaustive search across all possible games, then you have to look at, you know, every board, all of the branching moves, So if we start out, if it's like 765, and then there's like 9 moves,
For
and
every
then
action.
yeah, and then this ends up growing quite quickly. Although we can reduce the number of possible moves by 1 every step, but
Right.
we'll still end up with a much
Exhausting.
larger number. Yeah, I mean, we also luckily here have a limit to how long a game can be. Right, a game like each player can only make or well, like each like nine total moves for the game, but it's still a lot of branching. But that does conclude chapter 1. I'll do a little preview of chapter 2. Is really setting up things that will be relevant later, but for the moment, we're not going to actually consider these Markov decision processes, but we're going to greatly simplify the problem and just look at these multi-armed bandits. And these are stateless problems. So we're given a bandit problem. You could think of it as just a machine with a bunch of levers. And every time you pull one of the levers, it has some distribution of reward that it gives you. It could be a single number or a Gaussian with a certain mean. And we know that this is like a fixed distribution over time. However, we don't know what it is ahead of time. So for these problems, like we're presented with a bandit, or you could think of a bandit as just one of these machines. And the idea is, how do we, as efficiently as possible, figure out which lever gives us the most reward, right? If we knew that ahead of time, we just always pull that lever. But right, we need to actually figure that out. So part of the problem is we have to, at some point, try the different levers a certain number of times to actually get estimates of what they're, what kind of reward they give. And then that will be the subject of this entire chapter, K-armed bandit problem. So we can vary the number of arms. And the point of this chapter is to introduce the concept of the value function without all of the other complexities that exist in reinforcement learning.